Okay, so we are estimating this recurrence relation. T of n is equal to T of 2n by 3 plus T of n by 2 plus n square. So we want to see what does this evaluate to. Now, if we could use Master Theorem, now if you recall in the Master Theorem, we can only use it if it's of a certain form. So if we had a slightly different recurrence relation like S of n is equal to S of 2n by 3 plus 2n by 3, so underlying the same expression, plus n square, or if it was r of n is equal to r of n by 2 plus r of n by 2, that's 2 times r of n by 2, plus n square, then we could use that. Now we do analyze this and we say, okay, what we're trying to find is between r of n and s of n. So then let's try to analyze r of n or s of n. We start with s of n. So we say s of n is equal to 2 times s of 2n by 3 plus n square. We use the Master Theorem here. A is equal to 2, b is equal to 3 by 2, f of n is equal to n square. We observe that b square is greater than a. 1.5 square is 2.25, so that's greater than a in this case. Therefore, log of a to the base 2 is less than 2. Therefore, the f of n term will dominate. Therefore, s of n is equal to n square. Similarly, we solve for r of n, which also we can use using Master Theorem. So we get r of n is also n square the same way, which you might have already seen, because in this case a is equal to 2, b is equal to 2. Therefore, the f of n term dominates. So there you have it. In this case, we get very lucky. T of n is equal to, in either case, is going to be n square on the lower end, on the upper end. Therefore, T of n is n square. So sometimes we can use the Master Theorem to analyze a recurrence relation that's slightly smaller, slightly larger, and that's how we can solve for T of n.